going to start with section A, which is multiple choice. We have around about 10 questions, and each question carries 2 marks. Okay, so question number 1. They're telling us that there's a book that rests on a table. Which of the following forces will form an action-reaction pair? So an action-reaction pair is basically a pair of forces that must counteract each other. An example, if a book is resting on a table, we know that 1, there's going to be the weight of the book that will be acting on the table, and then the table in reaction to that must create a force that must act on the book. Okay, from Newton's third law, whereby action and reaction must be equal but opposite. So when we look at the options, they're telling us the force of the earth on the book. That's not true. The force of the book on the earth, that is also not true. The force of the book on the table, no. The force of the table on the book. So the correct option there would be option D. So I'll take D for question 1.1. And then 1.2. Telling us a person is standing on the bathroom scale in a moving lift. Which of the following motions of the lift will result in the smallest reading? Okay, when the lift accelerates upwards, when the lift accelerates downwards, when the lift moves upwards at a constant velocity, or when the lift moves downwards at a constant velocity. So I'm going with option B. When the lift is moving downwards, that's when the reading will tend to be smaller. Okay, we can explain that if we have, let's say, a free body diagram of the way that's acting downwards and then the normal reaction upwards. Now, if there is a lift now, and then there is also the weight of the lift, the fact that acceleration due to gravity will always act downwards, so the amount of force downwards will be less, so the reading will also tend to be smaller. Then 1.3, the velocity versus time sketch graph shows the motion of a ball which was in free fall. So for free fall, that is basically motion under the acceleration due to gravity only. So the ball struck the ground after 30 seconds. And then the question is, which of the following statements will be correct about the ball? Okay, so the ball was dropped from a height above the ground. A height above the ground. Okay, there's some bit of sense there. But when you say it was dropped above the ground, when we look at the graph, at a time t, the velocity is 0, which simply means that this ball moved up, reached its maximum, and then went back below the point of projection and so on and so forth. Okay, so this narrative of drop from a height, no, I'm refusing. It's not making sense. Not now. Then it was thrown vertically upwards from the ground. This is also not making sure, as much as the vertically upwards is correct. It was thrown vertically upwards from a height above the ground. Then it was thrown vertically upwards from a height, no, downwards from a height. So this is also out, because if it was thrown vertically downwards from a height, then we don't have a maximum height where the velocity is a 0. So this is out, the first one is out. We are left with just B and C. But now, since we are having issues with B, I'll choose option C to be the reasonable option there. Then 1.4, they're telling us the vector diagram below shows the initial momentum P1 and the final momentum P2, and then the change in momentum. So with vectors, we know that the length of the line always represents the magnitude. Okay, so we know that this positive magnitude is bigger since the line is longer. And then if we look at P2, we're seeing also a slightly smaller momentum compared to P1. Then remember, for us to get the change in momentum, it will be the P2 minus the P1. And since the P2 is smaller than the P1, that's why the direction is in the opposite. So which of the following sketch graphs correctly shows the momentum of the car for the time the car moved on the road? So you can see that initially the momentum was higher and then the momentum dropped. So which option is going to make sense? Option B is out because it's showing us that the momentum was lower than increased. When we look at option C, it was higher and then dropped into the negatives. Okay, and then it was lower and then increased. So D and B are out. Our problem now will be C and then A. So when I look at A, I think it would make the best option compared to C. Momentum just decreased because it shows the momentum of the car as it moved on the road. That's fine. Then 1.5, a stone of mass M dropped from a height h above the ground. Ignore the effects of air friction. Which of the following combinations correctly represents the kinetic energy? 1, and then 2, the total mechanical energy of the stone at the instant the stone has fallen through a distance of a quarter height. Okay, so what we can see is that if we have probably a building or a height h here, and then we are being told that the stone has fallen up to a certain height, which is a quarter h. We know that at the top of this height, the stone is going to have the maximum potential gravitational energy, and then 0 EK. And then at the height of a quarter h, the stone is going to have what we call mechanical energy, which is a combination of both the EK and the EP. Okay? But from the law of conservation of energy, we know that energy can neither be created nor lost. So the EP max at this height should be equal to the mechanical energy at this point. So let's get our EP max at a point h. Okay, know that EP is mass, gravitation, and the height. So you're going to keep it this way since we don't have any values. Then at a point, a quarter h, our EP is going to be a quarter h multiplied by the mass multiplied by the gravitation. So which means it's a quarter mgh. This is our EP. Now for us to get the EK, we just need to subtract this from this. So that is 1 mgh minus a quarter mgh, which gives us 3/4 mgh. So this is going to be my EK. Okay, let's read the question again. Stone of mass is dropped from a height of the ground. Ignore the effects. Which of the following combinations correctly represents the kinetic energy and the total of the stone at the instant has fallen through this? So we're not using the ground as a reference, we're just using the point of projection as a reference. So our mgh, or our EP, so EP is going to be a quarter mgh, and then the EK must be 3/4. So a quarter mgh, we said, so kinetic energy we said is 3/4. So which options are 3/4? We have A and then we have C. Then they are also asking for the total mechanical energy. We say total must be equivalent to EP max. So I'll go for option C. Option C. That is showing us the kinetic energy and the total mechanical energy. Okay, so C is the correct option for 1.5. And then 1.6, they're telling us a spectrum of helium emitted from a star moving away from the Earth is compared to the spectrum of helium that is found on Earth. Which of the following statements is correct? The observed line spectrum from the moving star will have blah, blah, blah. So the star is moving away. So for as long as it is moving away, number one, what we need to remember is that the wavelength is increasing, okay? And then for as long as the lambda increases, okay, the frequency must decrease from V or from C is equal to F lambda. We know that if I make F the subject, it will be C over lambda, which means the two are inversely proportional. So what I'm going to say is that the frequency is lower, the wavelength is longer. 1.6, I'll go with option A. Okay, so A is my option. Then we move on to 1.7. Talking about the magnitudes of electric fields generated by different point charges and measure a fixed point. For each measurement, the distance between the fixed point and the charges are the same. Okay, which of the following shows the correct representation for the relationship between the magnitude of electric field and then the charge? So from the formula of electric field, we know that it is F over Q. Then when you replace this F, Coulomb's law of electrostatics, Q1 over Q2 over R squared, and then you're dividing it by Q. So this Q cancels that Q, so which means you're just left with KQ over R squared. So you can just get this from the formula page straight away. Okay, so we can see that the electric field is directly proportional to the magnitude of the charge. Okay, so option A will be perfect. So as the Q increases, so will the electric field. All right, then 1.8, the diagram below represents a circuit in which all the external resistors have the same value. Okay, let me take this to be 2 ohms. Everywhere, 2 ohms, 2 ohms, 2 ohms. Then the question is asking, write or which one of the ammeters in the circuit will have the lowest reading. It's in capital letters. So we have an ammeter here, this A, will give us the reading of the current within the circuit. Okay, so we expect this current to be bigger than this and that. Same applies with A4. So A1 and A4 are going to have the same readings since they are just connected to the circuit outside. They are not affected by these resistors. But we know that this resistor here and this one, they are in series, okay? But then these two form a parallel combination with this resistor by A2. So if I combine these two, it's going to be like 4 ohms, which means the resistance here is going to be bigger compared to the resistance here. So which means there's going to be less current that is flowing via this route. So the reading of the ammeter with the smallest value will be the A3. So I'll take C to be my option. Okay. And then 1.9, the following diagram is an electrical machine which is shown below. Okay, what type of machine is this? So before we draw the conclusion, we need to see which features are surrounding this machine. Number one, we have a source of energy, which is maybe a battery or something. So this is a DC source. So for as long as there is a DC source, it cannot be a generator. So C is out, D is out. Now, by virtue of the rings are split. Okay, so for as long as the rings are split, then this becomes a motor. So this is going to be a DC motor. Okay. So splitting the rings becomes a DC motor. Okay, so option A is 1.9, and then 1.10. Which of the following combinations is correct for a line absorption spectrum in terms of the energy transitions of the atoms and the appearance of the narrow lines? Okay, so we know that whenever there is an absorption spectrum, like for as long as the particles or the electrons gain energy, they'll move from lower energy levels to higher energy levels. Okay, so option A is out, that is moving from lower, that is when they lose. That will be like emission. So this one is also out. So I'm going to focus on B and C, where there is lower to higher. Okay, and then what is the appearance of the narrow lines within that? Are they going to be colored or are they going to be dark lines? Correct option is C. They are going to be dark lines. Okay, they can be of different sizes, but they will be dark lines. So that is how question 1 would be answered. All right, so we move on to question number 2. Okay, so question number 2, they're telling us that block A of mass 4.1 is connected to block of mass 0.3 kilogram by an inextensible string passing over a frictionless pulley. Block A is at rest on a rough horizontal table and block B hangs vertically as shown in the diagram. So we have a frictional force. Okay, so frictional force is 49 newtons, and then it is applied to block A at an angle of 50 degrees to the horizontal. Okay. Okay, and this causes the block A to accelerate to the left. Okay, so which means everything is moving to the left. And then they also gave us the coefficient of kinetic friction to the surface to be 0.35. Okay, so with all these details, we just need to... Okay, so which means the entire system is moving in that direction. Okay, then 2.1, they're asking us to state Newton's law, second law in words. Okay, so what we know about Newton's second law in words is that when a net force, let me just try to write it here. Okay, so we're saying when a net force acts on an object, the object will accelerate. Okay, object will accelerate in the direction of the force. Will accelerate in the direction of the force, and the acceleration is directly proportional to the force and inversely proportional to the mass of the object. Okay, so that would be your 2.1. And then 2.2, they want us to draw a free body diagram that is showing all the forces that are acting on A as it accelerates to the left. So looking at A, we can see that there is going to be normal force, there is going to be weight that is acting downwards, and then there is going to be this applied force. Remember, the surface is also rough, so there is going to be a frictional force acting in that direction, but there is also this tension force. Okay, so since we're having 5 marks, we should expect something like 5 forces. So 1, 2, 3, 4, then 5. So I'll just try to draw that free body this side. So if that is my body, we say there's tension and then there is frictional force, and then there is the normal force, then we have the weight, and then we're going to have our force applied somewhere there. So this becomes our free body for this particular diagram, for that particular question. And then we move on. So this is 2.2. Alright, 2.2. Then we move on to 2.3. 2.3 is asking us to calculate the magnitude of the frictional force that is exerted on block A. Magnitude of the frictional force that is exerted on block A. Okay, so when we look at the body A itself, okay, we can see that this applied force is at an angle, so it has the components. Okay, so if I'm to break this down, okay, I'm gonna have this and then that, okay, into two components. So this is going to be the F, the sine of 50, and then it's gonna be the applied force, the cos of 50. Okay. Then I know that the upward motion weight is equal to the normal force plus the F sine of 50. You know the F is 49, okay? But now we want the normal reaction. Normal reaction is going to be the weight minus the F sine of 50. Okay, so we need to highlight this first. Then we know that the frictional force is given as mu multiplied by the normal reaction. Okay, so I'm going to jot it this side and say that my F is mu times the normal reaction, but we say that N is the same as weight, okay, minus the F sine of 50. Do the substitution, that's going to be 0.35 because we were given the mu, the coefficient of friction as 0.35, okay, into our normal reaction, which is given as that. So the weight is going to be mass times the 9.8, because we know that weight is given as mg. What is the mass of the body? Is 4.1. Okay, so that's going to be 4.1 times 9.8 minus 49, the sine of 50. Okay, so when I punch this into my calculator, times 9.8 minus 49 sine of 50. What is it? So I end up with 0.925. Let me just round it up to 2 decimals. So 0.93 newtons as my frictional force. Then 2.3.2. They want us to get the acceleration of block A by applying Newton's second law on each of the bodies or the blocks separately. Okay, so if I'm to look at that, we know that Newton's second law is going to be F net is equal to ma. What is the question asking for? The acceleration, which is the A. Okay, so for as long as the body is moving, then we're going to apply the F cos and then the F. Okay, so let's start by looking at body A with the motion. Okay, body A is going to have F cos of 50. It's going to have the tension and then the frictional force in that direction. Okay, this is A. When we look at body B, it's just the tension and then the weight. Okay, so those are the only forces that will be acting on the two bodies respectively. So I can start by looking at body B. Okay, and say that when I look at body B, since it's moving to the left, which means the tension is going to be greater. Let me start by writing the formula that F net is equal to ma. Okay, just to get the mark for that formula. And then if we do the substitution, it's going to be tension is going to be equal to, no, I'll set tension minus the weight should give us the MA. Our tension we don't know, but then the weight is going to be 2,3 times 9,8. Okay, 2,3 multiplied by 9,8 should give us 2,38. I can move all of this to the other side. So I'll get 2,3 times 9,8, which becomes 22,54. So I'll have 2,3A minus 22,54. I'll call this my equation number 1. Then I'll look at body A. Still apply the same thing. F net is equal to MA. So remember we said it's going to be the F cos of 50 minus, I don't want to bring in the cos 180s and so. So let me just say minus, since I know that the tension and the friction are just in the opposite directions. Okay, so minus the frictional force, okay, minus the tension, must give me the mass and that. When I do my substitution, okay, this was a 49 cos of 50 minus the frictional force, we got 0,93 minus tension. Okay, we say tension is that. That's fine, let me just do that. Is equal to the mass, we said it's 4,1. Good. That's going to be 4,1A. Let me make T the subject so that I can equate both equations. Alright, so when I simplify these two, I have 49 cos of 50. I'm subtracting 0,93. That gives me 30,567 minus T should give us 4,1A. I'll move the T that side, I'll move this on this side. So 30,567 minus 4,1A should give us a T. Then I'll call this equation 2 and equate both equations. So 2,3A minus 22,54 should give us 30,567 minus 4,1A. I'll collect the like terms. I'll move the 4,1 this side. I'll move the 22 this side. So 2,3 plus 4,1, that gives me 6,4A. I move this side, it's going to be a plus, so 30,567 plus 22,54. I'm getting 53,107. Then I'll divide both sides by 6,4. Does that make sense? Did I do anything wrong? Anything wrong? Anything wrong? That makes sense for me. It's not going to make sense for me. Let me just go back and revisit this thing. Let me see. We said 31.5. Why am I having 30.5? 49 cos of 50. Yeah, my numbers are not correct. Let's start with 2,3 times 9,8. Okay, so this is fine. Let's come here. We say we are saying did I do anything wrong? Is there anything that's not making sense? Did I leave out any force? Let me just go back to my free body diagram and see. Remember, we said we have this, which is applied tension, and then there is also friction. Okay, so I think this is meant to be a plus as our equation number 1. So I'm going to put a plus there, because when you transpose this negative to that side becomes a positive. So the rest is fine. So we're going to subtract that. We're going to have a 30,567 minus 22,54. Let's not divide yet. Okay. So it will be 6,4a is equal to 30.567 minus 22,5, which gives us 8,027. We now divide both sides by 6,4, divide by 6,4, and then our A becomes 31.25 meters per second squared. Okay, this makes sense. Okay, then next question. Oh, that is it. That's all. It's question number 2. Because they only wanted the acceleration. Alright, then we move on to question number 3. Question number 3, we're being told that a hot air balloon moves vertically downwards at a constant velocity of 3,4. Okay, so if the velocity is constant, acceleration is going to be 0 for the balloon. When the balloon is 15 meters above the ground, a small ball is dropped. Refer to the diagram below. Okay, so since the balloon is moving downwards and then the ball is dropped, so the ball needs to continue with the motion of the balloon as initial, just from the law of inertia. Okay, so there's no reaching maximum height and then turning and so on. Okay, we go on and say that the ball strikes the ground and bounces vertically upwards. The hot air balloon continues to move downwards at the same constant velocity. Ignore the effects of air friction, and then they want us to define what the term fall is. So we know that free fall is a body, or it's just a motion. It's a motion, we can say, under which acceleration due to gravity. Acceleration due to gravity is the only force acting on the body or the object. So, or you can say it's the motion during which only force acting on the object accelerates gravity. Whichever way, as long as we get to know that it's only acceleration due to gravity that's acting there. Then the sketch below represents the positions of the ball relative to the ground. Okay, the time it was dropped up until it reaches maximum height at the first bounce. Okay, then the question is 2.3 points. Was the ball in free fall between T1 and T2? Just write yes or no. The answer is a no. For as long as the ball leaves the air and touches the ground, it's no longer free fall. Okay, because the force that is entirely there is not only acceleration due to gravity. So the answer there will be a no. And then 3.3, they want us to get the value of T1. So T1 is the time when the ball strikes the ground. How do we determine that? So we know that the initial velocity of the ball was 3,4 meters per second, because that is the velocity with which the hot air balloon was moving. So from the equations of motion, what I can do, I'll just jot it inside and say 3.3.1. I can use now my change in y. Okay, is given as the v delta t plus a half a delta t squared. Write the formula for your mark. Since the stone or the ball fell through 15 meters, so our change in y is going to be a 15. We're looking for the t, but the initial velocity was 3,4. Let's do the substitution. So change in y, we're saying is a 15. Okay, is equal to 3,4 delta t plus a half. We know that the g is the same as the a, which is 9,8. Since it's moving downwards, I'll take it to be positive, then multiply it by t squared. When I simplify this, I'll get 4,9t squared plus 3,4t minus 15 is equal to 0. Now, when I use my quadratic formula of negative b plus minus square root of b squared minus 4ac over 2a. That's going to be negative 3,4 plus minus square root of 3,4 squared minus 4, the a is 4,9, the c is negative 15. Divide this by 2 times 4,9. So the first answer I get is 1,44 seconds, and then the second answer I get is negative 2,13. But we know that time should never be negative. Therefore, the t is going to be 1,44 seconds. Okay, so that is 3.3.1. Then 3.3.2, they want us to get the height, the hot air balloon above the ground at the instant when the ball struck the ground. So, we know that we shall be using the time that we obtained. This is 3.3.2. Okay, so the time is 1,44 seconds. Now we need the displacement, which is delta y. We know that the acceleration is going to be a 0 since there is no change within the velocity. Okay, so if I use still the same equation of delta y is equal to vi delta t plus a half a delta, that squared. Remember, the balloon is not in free fall, it's having a velocity. So the acceleration here is a 0, which kills this entire thing. So we're looking for change in y, which will be the 3,4 multiplied by the 1,44 plus, that's a 0. So 3,4 multiplied by 1,44, that gives me 4,896. I'll just call it 4, okay, let me just write everything there. 96 meters. But the question is asking the height of the air above the ground. So the hot air balloon would have moved this towards the ground. So the height above it will be 15 minus 4,896. Okay, so I'll say 15 minus the answer. I'm getting 10,104, which is like 10,1 meters. All right, so that is 3.3.2. And then 3.4, the ball was in contact for just 2 seconds and then left the ground with an upward velocity of 7,2. Use the equations of motion to calculate the value of T3. Where is T3? So at T3, that's when the ball reaches the maximum height. But we know that at maximum height, the V final is 0. They gave us the V initial to be 7,2. Let's determine the maximum height. We don't need the maximum height, but just the time within which the ball reaches the maximum height. So 3.4, we're saying that at maximum height, after the bounce, the V final is 0. The V initial was 7,2. What we want is the delta t. The ball will be moving with 9,8, which is the same as the acceleration. Okay, so we can use the first equation of motion. V final is equal to V initial plus a delta t. Let's do a substitution. That's a 0. V initial is 7,2. Is that correct? Yes. And then plus, since the ball is moving now upwards, I'm going to take the a to be negative 9,8 multiplied by delta t. So move the 9,8 that side, saying 9,8 equal to 7,2. I'll divide by 9,8 divided by 9,8. Okay, 7,2 divided by 9,8. I'm getting 0,735. 0,735 seconds. Okay, so that is the time it took the ball to reach the maximum height. So now if this time the interval here is 0,735, the interval in between is 0,2, and then from there to there is 1,44. You need to just add up all the three values to obtain the actual value of T3. So T3 is going to be 1,44 plus 0,2 plus the 0,735. If I do my additions, I'll have 1,44 plus 0,2, which gives me 2,37. Okay, seconds. Just jot it aside. We shall say 0,735 plus 0,2 plus 1,44. So it's 2,37 seconds. All right, so that is question number 3. Let's look at question number 4. Being told that trolleys A and B of masses 3,2 and 2,6 respectively are held at rest on a horizontal friction less. Okay, in other words, there is no friction there. With a compressed spring between them, okay, after the trolleys are released, the spring extends its natural length, then falls onto the trolleys. Trolley A now moves with a constant velocity of 0,4 to the left, and B moves with a constant unknown to the right. B reaches the end after a time of 1,3 seconds. Okay, state the principle of conservation of linear momentum. So this simply tells us that the total linear momentum, okay, total linear momentum of an isolated system, remains constant, or you can tell us is conserved. All right, then 4.2, they want us to calculate the distance that is traveled by trolley B. Remember, they told us it traveled that distance in 1,3 seconds. Initially, it was at rest, so the V initial is 0. But before we can get the distance, we need to get at least the V final. For us to get the acceleration, at least we need the final velocity. So we can apply the conservation of momentum and then get our V final before we can determine what the question wants. Okay, so that is 4.2 that we're answering. So 4.2, we're going to say that momentum before, or the sum of momentum before, must be equal to the sum of momentum after, which is mass of A, V initial of A, plus the mass of B, the V initial of B, should give us the mass of A, the V final of A, plus the mass of B, the V final of B. So the mass of A is 3,2. Okay. Initially, it was at rest. Mass of B is 2,6. Initially, it was at rest. Is equal to the mass of A, which is 3,2, but then the velocity of A is 0,4 in the opposite direction. So I'm going to take that to be negative 0,4. Plus mass of B, which is 2,6 times the V final B that I don't use. So play with that. That's going to be 3,2 multiplied by 0,4, which gives me 1,28. Negative 1,28 plus 2,6 VFB must give us a 0. So I can move this to that side. 1,28 is equal to 2,6 VFB. Divide both sides by 2,6 by 2,6. So my final velocity of B becomes 0,49 meters per second. Okay. Now, having obtained the 0,49 meters per second, now I have my velocity. final. Then I can go down and determine my displacement. Okay, so I cannot use the first equation of motion, but I can use the last one, which is V final squared is equal to V initial squared plus. Will this help me? Because I need 2A, then the displacement. Do I know the acceleration? I can get the acceleration though. I can get my acceleration, but that is going to take some bit of time. Okay, if I get the acceleration, V final minus V initial over delta t. Our final is 0.49 minus 0 divided by 1.3. 0.49, 0.49. But why not use the first one? V final is V initial plus A delta t, but we need the acceleration. Fine, let me use this. 0.49 divided by 1.3 seconds. That gives me 0.377 meters per second squared. And then I can just substitute there. So V final 0.49 squared is equal to the 0, which is the initial, plus 2 multiplied by the 0.377, then multiplied by the delta x we need. Then I can get the 0.49 squared. Why don't I just say delta x is 0.49 squared divided by 2 times 0.377 straight away. Okay, 0.0.049 squared, dividing it by 2 times 0.376. I get 0.318 meters. 0.318. This is one approach. If I use that other approach of speed is equal to distance over time, we need the distance, the speed. That's going to give me a little bit bigger, which is 0.49 multiplied by, said 1.3. Is that correct? Yes. 1.3. What do we go with? Calculate the distance of vector V in this time. Initial at rest, and then final velocity is 0.49. So what would be the acceleration? Guys, I'm going to go with that. I am going to go with that as my answer. Alright, so 0.318 meters. That's the displacement. And then the next thing that the average force exerted by the spring on which trolley while they are in contact is 4.2 newtons. Calculate the time it took the spring to exert the natural length. So the average force when they were in contact. So this is more like the impulse. Or you can use the impulse formula anyway, whereby F net should be equal to the impulse, which is like changing momentum over changing time. The question is asking for the time. So that's going to be 4.2 is equal to the change in momentum. I can use 2.6. Okay, we know that 2.6 is for B. Our final velocity is going to be 0.49 minus 0 divided by delta t. I'm going to get my t alone. It's going to be 2.6 multiplied by 0.49. I'll divide it by 4.2. If I punch that into the calculator, 2,6 into 0,49, dividing it by 4,2, that becomes 0,30. Okay, so delta T 0,30 seconds, or 0.303 seconds. All right, question 4.4, trolley P is now replaced with trolley C, which has a larger mass. Okay, and then the same compressed spring is replaced, or is placed between trolleys A and C, and the trolleys are then released. The average force exerted on the trolleys remains as 4,2 newtons for the same period of time as calculated in 4.3. Okay, how does the magnitude of the velocity of trolleys compare to the magnitude of velocity of B that was initial? Okay, let's see. Let's. So the question is asking for velocity. So one thing we know is that the force is the same, and we know that force is directly proportional to the mass as well as the acceleration. But since the track is stationary and we are applying it to a heavier mass, what do you think the logic would be? How does the magnitude of the velocity C compare to the magnitude of P? So we think that this gave us a magnitude of 0,49. So if the mass is bigger, which means the velocity is going to be smaller. So they say greater than, less than, or equal to. So we say it's going to be less than. The reason is going to be increasing the mass, okay, will increase what we call the momentum. Will increase the momentum. But we know that mass is inversely proportional to velocity. We know that momentum is mass times velocity. So if we make m the subject, it's going to be momentum over v. So mass is inversely proportional to velocity. So increasing the mass will lead to an increase in this. But since mass is inversely proportional to that, so increasing mass leads to a decrease in the velocity of the body. Alright, so that is 4.4. In question number 5, we're being told that a crate of mass 18 kilograms initially at rest slides down a frictionless slope from A to point B, and the crate moves along a rough surface. Okay, so there's a rough surface there. Towards point C, point A is 3 meters above the horizontal surface in the diagram below. State the principal conservation of mechanical energy. So, sorry, is the same. Total mechanical energy in an isolated system remains constant. Okay, or you can tell us it's conserved. And then 5.2, using the energy principles only, calculate the speed of the crate and the energy principles. So energy is conserved. So one thing we know that at point A, when the crate is at rest, it will be having EP mix. The EK is going to be a 0. At this point B, the lowest, the EP is going to be a 0, and it will be just having the EK max. So since we want the speed, we have to use the EK. Since there is conservation Whatever is here must be to that. So we're going to say that at A, we have the EP max and EK 0. And then at B, we have the EK max and EP being 0. But from conservation, the conservation of energy, or from the energy principles, we can say that the EP max must be equal to the EK max. This is at A and this is at B. So MGH must give us a half mv squared. Now since we're dealing with just the same body, we can just cross out the masses. It's fine. So that's going to be 9,8 multiplied by the height, which is 3 meters, should give us a half v squared. Multiply both sides by 2. So this cancels that. We have 2 times 9,8 times 3, which gives us 58,8 is equal to v squared. And then I'll have to find the square root. And then my velocity there is going to be getting 7,668, which is 7,67 meters per second. Okay, so that is 5.2. And then they are telling us that there is a constant frictional force of this much that is acting on the crate as it moves from point B towards C. And then the crate comes to rest at point C. So which means our V final here is 0. Our V initial there is 7,67. All right, take the work energy theorem. So we know that this simply states that the work done on an object, by a net force is equal to the change in the object's kinetic energy. Okay, the work done on an object is equal to the change in the kinetic energy. And then they want us to use the energy principles again only to calculate the distance that the crate traveled from point B up to point C. Okay, so let me just get down here. This one. So we know that W net must be equal to the change in EK, which means that our W net is equal to the EK final minus EK initial. So as this body is just continuing to move, the only force that is acting on it will be this frictional force, so that it comes to a rest. And it's going to be acting in the opposite direction. So I'm going to look for the work done by all the forces. And the work done will be just by the frictional force. So I'll say frictional force multiplied by the delta x. Okay, because that's what the question wants. And then multiplied by the cos of 180. This should give us the EK final, which is going to be like a half mv final squared minus a half mvi squared. So our frictional force, they gave it as 40,6. Okay, 40,6 multiplied by delta x, and then the cos of 180 is equal to a half. The mass is 18 kilograms. Good. Times 18 multiplied by 0 minus a half times 18 multiplied by 7,67 squared. Okay, so on this other side I'm going to have negative 40,6. Delta x is equal to negative, that's going to be 9 multiplied by, let's just say 7,67, but squared, that becomes 529. 13.46. Divide both sides by negative 40.6. Negative 40.6. This cancels that, which means our delta x is going to be 40.6. It's going to be 13.04 meters. Okay, so that distance is 13.04 meters. Then 5.5, we're being told that the height of the track is now lowered. So that point A is at a vertical height of less than 3 meters. Okay, so somewhere here or below. Okay, point B. Then same crate again is released from point A. How will the distance now traveled by the crate along the horizontal surface before it comes to rest compared to the distance that is calculated in 5 meters? Right, only greater, smaller, or equal to? Now we know that since the energy that we are dealing with is dependent, okay, so EP is directly proportional to the height. If you increase the height, you increase the energy, okay? Likewise, since the EP was the same as the EK, increasing the height will increase the EK. Now, the moment you reduce the height, you're reducing the value of the EP, you're reducing the value of the EK, which means the velocity with which the crate is going to move, or the crate is going to have at point B, is going to be smaller. And if the velocity is smaller, which means it's going to take a shorter period of time before it comes to rest, which means the distance that is going to be moved is going to be smaller than. Okay, so here we're going to say smaller than. Then you can say that a decrease in height, okay, decrease in height will lead to a decrease in EP and EK, which lowers the velocity and then thus the distance moved or the distance traveled by the crate is smaller or smaller than. Just something of the sort of. So that is question number 5. Question number 6. Question number 6, they're telling us we have a stationary listener that records the frequency of sound emitted by a siren of a police car when the car is traveling at a constant velocity of approaches the listener. This is what was recorded. Okay, we can say that towards the listener, the frequency of the listener is 615. Then the car passes the listener at P.1 and then moves away from the listener recorded. So when you're moving away, the frequency is 526. And then they want us to state Doppler effect in words. So we can say the apparent change. Okay, so apparent change in the frequency of sound detected by the listener because the sound source and the listener have different velocities that are relative, different velocities that are relative to the medium of propagation. Just that. Then use the information to calculate the speed of sound in air. So this is a long question, but it's fine. We shall attempt it. Okay. So we're going to start by writing down the Doppler formula, where we know that the frequency of the listener is equal to V plus minus the VL over V plus minus the VS multiplied by the frequency of the source. Okay? Now we have two scenarios. When you're moving, or when the police car is moving towards, what is the recorded frequency? We said it was 615. Okay, 615 is equal to V that we need plus the velocity of the listener, which is a 0, over V. This is going to be minus 26 times the frequency of the source, which we don't know. When I play around with this, when I have 615 into V minus 26 is equal to F S times V. Can make Fs the subject. So that is 615 into V minus 26 divided by V. Call this equation 1. And then let me look at the other scenario where the police car is moving away. Just from the same equation, I'll just say 526 is equal to V minus 0 over V plus 6 times the frequency of the source. Do the same thing. 526 into V plus 26 is equal to V multiplied by F. Why can't I just simplify? We can't. This is VFS, VX, because it's the same velocity of the sound that I'm looking for. It's the same frequency that is being used. Call this equation 1, guys. She's just making life hard. I'll call this equation number 2. Then I'll equate the equation 1 is equal to equation 2. Then I'll try to open this. It's going to be 615V minus, we have 615 multiplied by 3. That gives me 15990 is equal to 5263 plus, that is 26 times 5, which is 13676. I'll collect my like terms. I'll move this side. I'll move this side. So 615 minus 526. That gives me 89V. Is equal to. It's gonna be 13676 plus 15990. That gives me 29666. Then I'll divide both sides by 89. Okay, so divide this by 89. I'm getting 343,325. Okay, also meters per second. That's what I get. Then calculate the wavelength of the sound emitted by the police siren. So we know that V is equal to F lambda. Okay, F lambda is the wavelength that they need. Do we know the frequency of the source? No, but we can get it. Okay, so since we had already created this equation, we can use it and say frequency of the source 615 into the 333 minus 26. I'm dividing it by the same velocity, which is 333,33. Punch that into the calculator. 615 into 333,33 minus 26. We are dividing it by 333,33. This gives me 567.03 hertz. Okay, so we know that V is equal to F lambda, which means that lambda is going to be V over frequency. So we know that the V was 333,33. Now I'm dividing it by this 567.03. 0.03. Okay. So what do we end up with? What do we end up with? So 343.33. Dividing it by 567.0 that. So that gives me 0.588 centimeters. Okay, so that is the wavelength that the question needed. And then 6.4, sketch a graph of the recorded frequency versus the time of the motion. Okay. This is frequency in hertz. Then this is going to be our time in seconds. One thing we know is that we need, as the motion of the car moves towards and passes the listener and moves away, label T1 as the time, no values are needed. So frequency versus time of the motion of the car as it moves towards the listener and then away. So we just need the observed frequencies. Remember we had the 615 and then the 526. Yes. So the frequency started by being there. And then at the time T1, the frequency dropped to there. So this is what we need. And that is all. We don't need any values. Okay, so that is question number 6. We move on. Question number 7. X is a point that is 0.025 meters away from a 4 nanocoulomb charge. Then they want us to draw the field pattern due to this. So it's a positive charge. Yeah. Okay, we know that the field lines must be moving out. And then the arrows must be just in the direction. Okay, so that is what we have to do with 7.1.1. Then 7.1.2, calculate the magnitude of the electric field at X. So we know that electric field is given as E is equal to KQ over R squared. Okay, so our K is 9 times 10 to the 9. Our Q is 4 times 10 to the negative 9, since it's nano. And then we are dividing this by 0.025 squared. Okay, so when I punch this into my calculator, I'm having that much over 0.025 squared, which gives me 5,600 Newton per Coulomb. Okay, then 7.2. 7.2. Two identical neutral polystyrene balls A and B are suspended from a ceiling by insulated strings of equal length as shown in the diagram. Okay, they are hanging nicely. And ball B is given an initial negative of QB, some unknown magnitude. Then the balls attract each other, touch, then repel each other. Okay, and they get rest. Centers 10 centimeters apart, so that each string makes an angle of 90 degrees with the vertical, as we can see that. All right, then 7.2.1, they want us to state Coulomb's law in words. Okay, so with Coulomb's law, we can say that the magnitude, I'll just start it from here, and we see that the magnitude of the electrostatic force, okay, magnitude of the electrostatic force exerted by 1 point charge on another is directly proportional, okay, directly proportional to the product of the charges, the product of the magnitude of the charges, magnitude of charges, okay, inversely proportional to the square of the distance between them, the square of the distance between them. Okay, then 7.2.2, they want us to calculate the magnitude of the initial charge qubit, given that P is having this mass. Okay, so what I notice, or what I can see that could probably help me, is if I look at this ball at this point, I believe there is a tension force there. If that is a 9, which means if I draw a vertical line like that, this must also be a 9. Which means there are two components that are acting here. Okay? So we have the T, this is going to be cos 9. And then we have the T, sine of 9. So we know that the T cos of 9 must be equal to the weight of this body, of this ball. And then if I look at the horizontal, since there is repulsion, okay, of the forces, this one is pushing this side and this one is also pushing that side. Does that make sense? No, it doesn't. But it makes sense. Whereby this force is acting that direction, force is acting that direction. Which means that the TS9 must be equal to that force of the repulsion. Okay, so that's the scenario that I'm looking at. First, the magnitude of the qubit. So I can start by finding the force between them at this point when they are separated. Okay, so we know that it's K, Q1, Q2 over R squared. The force is what we need. Okay, that's 9 times 10 to the 9. And then I'm going to multiply it by Q squared, since both are having the same magnitude of charge. Then I'll change this to meters, which is 0.1 squared. Okay, I can call that my first equation. Then I come down and play around with another equation, whereby T cos of 9 gives me the weight. Then for me to get the T, I'll get the mass, which is 0.012 multiplied by 9.8 over the cos of 9. Okay, then what answer do I get here? So 0.012 times 9.8, dividing this by the cos of 9. This gives me 0.119 newtons. Okay, then I'll go to the horizontal part and say, but my F, okay, is the same as T sine of 9. Okay, so where I see F, I'm just going to replace it with that. So T, we already have the value, so it's going to be 0.119 sine of 9 should give us 9 times 10 to the 9 Q squared divided by 0.1 squared. Multiply both sides by the 0.1 squared divided by 9 times 10 to the 9. Okay, I need to get the value of Q squared alone. Okay, so I'll end up with Q squared being, let's see, 0.11 9. Sine of 9, I'm multiplying it by 0, 1 squared. And then I'm dividing it by 9 times 10 to the 9. Okay, this gives me 206, 84 times 10 to the negative 16. Then I need to find the square root. Okay, square root of the answer. Oh Lord, why is it such a big question? So big and answer is so small. So 1, 2, 3, 4, 5, 7. Okay, so I have 1,4. 1,4 4 times 10 to the negative 7. But this will be coulombs. So that is just the Q. But then the question is how much charge was initially given to that. Remember, this Q that we are getting is what the bodies will have after the separation. Remember, before they separate, there is a Q on A, there is a Q on B, and then they have to separate. Okay, so which means if I get the Q on A plus the Q on B divided by 2 must give me what is on B. But since A was neutral, there was no charge there. So I just have to multiply this answer by 2. So my answer multiplied by 2 gives me 2,88. So 2,88 times 10 to the negative 7 coulombs. So that is what I'm having. That is what I'm having as for now. Alright, so that is with that question 7. Question number 8. Battery of EMF 12V and internal resistance 0,2. Okay, is connected to 3 resistors, voltmeter, and then 2 switches, then some wires. Then the resistor Y is twice Rx. So this is the same as twice X. Okay. Then when both switches are closed, the reading of the ammeter is 5.5. So when the two are closed, we are given that. Can you give a reason why there is no current flowing through RZ? So what we can notice is that for as long as there is a switch over RZ, current tends to take a route with less resistance. Okay, so we know that current will just follow this route instead of going through this obstacle, which is the resistor. And that is the reason as to why the current will not go through it. So in other words, it's just a shortcut. What is going to be the reason? We're going to say that current uses a shortcut with no resistance. Shortcut via S1 with no resistance. Alright, and then 8.2, they want us to get the resistance of Y. I can just write it up here. So when both are closed, which means we only have these two to be working. And then the current is 5.5. So what do we do? What do we do? Now, since we have our EMF, we can use the EMF formula, but let me first get the external resistance. And since the two are in parallel, I'll get my R effective as product over the sum. So it's going to be Rx plus, no, it's going to be Rx times 2Rx divided by Rx plus 2Rx. So that's going to be 2 Let me just say x squared over 3x. 1x cancels that, so it's just going to be 2 over 3x or Rx. This is my effective resistance. Now when I apply the EMF formula, which is I into R plus small r, our EMF is 12, our I is 5,5 into 2 over 3x plus 0,2. So start by dividing both sides by 5,5. So 12 divided by 5,5 gives me 2,18. 18. Let me use it. Is equal to 2 over 3x plus 0,2. I'll move the 0,2 that side by subtraction, which means that the combination of the parallel is giving me 1,982, which is equal to 2 over 3x. Then I'll divide both sides by 2 over 3 divided by 2 over 3. And then the answer that I'm getting for x is 2,67 ohms. Okay. But now the question is asking for resistance Y. So which means this is going to be 2 times 2,67. All right, so that gives me 5,35. 5, is that is what I'm doing. Set 1,982. Okay. Multiply by 3, divide by 2. I get 2, there's a problem, guys. What's wrong with my calculator? Getting a different answer. It's 2,973. So which means I need to multiply this with 2,973. Okay. Which gives me 5,95. 5,95 ohms. Let's see again. 1,982. Said we are dividing it by 2 over 3. Oh, I did not use the bracket. 2,975. Which makes sense. So then 8.3 calculate the power dissipated by Rx. Still under the same scenario. So when we look at Rx, we said it is 2,975. It's approximately 2,98. Oh, around about 3 ohms. Okay. They want us to get the power there. So I don't have anything to do with current. I know nothing about the current here. So all I need to get is the external PD or the voltage. That is what's going to help me here. Okay. So how do I get my external voltage? I'll have my EMF, which is 12. Okay. Now let me get the internal one first. That's going to be easy. So V internal is going to be 0. How is that going to help me though? 0,2 times 5,5. We have the current already. Okay, 0,2 times 5.5. 5.5. Hello, it's 1,1. Okay, then I'll get external as 12 minus 1,1. Okay, that gives me 10,9. So that is the voltage across. Remember, this is parallel. So the same. Then for me to get the power, I can use V squared over R from the power equation. So my V squared is 10,9 squared over the R, which is 2,975. 2,975. Okay, when I substitute into the calculator, 10,9 squared dividing it by 2,975, that gives me 39,94. 39,94 if you round it off. That is watts. Okay, so that power is plotted. Let's move on. Now, both switches are now opened. Both switches are opened. Okay, and the reading is this. Now, if this is open and this one is open, it simply means that the current that is coming is just going through RY and it's also going through RZ. So these two are in series. And we know that the current will just be constant, which is 1,3, and the current here is also 1,3. What's going to be different is the potential difference across two resistors going to be different, but it will be equivalent to this external resistance, the external voltage 10,9. Okay, so what do they want? They want the reading on the voltmeter. But we know that the voltmeter is only connected across RY. So what I'll do, I'll just say my V is equal to IR from Ohm's law. So that's 1,3 multiplied by the RY, which was 5,95. Okay, 1,3 multiplied by 5,95, that gives me 7,74 volts. Okay, and then switch S1 remains open while S2 is closed. Okay, now the moment they said S1 remains open while S2 is closed, let's see. The moment they open that, which means now all the three resistors are playing a role within the circuit. What does the question want? The reading of the ammeter. The reading of the ammeter is what we need. Okay, all right, let's see. So what we can start with is looking at the two scenarios of where all the three resistors are playing a big role. We already know the value of this resistor. We know the value of this resistor, which is 5,95. But I think we can still use this 1,3 to help us determine the resistance of RZ. That's what I'm saying. Now, since the total, that's not going to make sense. Let me use this 1.3 now as my current. Okay. So which means the EMF is I into R plus the small r. Our EMF was 12. The current is 1,3. Now this R is going to be the R effect, which is the external. I'm adding the 0,2. Divide both sides by 1,3 first. So 12 divided by 1,3. 12 divided by 1,3. That gives me 9,23. Okay. 9,23, I'm subtracting 0,2. 9,23 subtract 0,2. That gives me with 9,03. So this is the resistance effective. Okay, the effective resistance across. Now, we know that Y and Z are in series, but already Y is 5,95. So for me to get RZ, it's going to be 9,03 minus 5,95. Is that okay? Okay. Then we say we subtracting 5,95. That gives us 3,08 ohms. Okay. So this is a 3,08 ohms kind of scenario. All right. What I need is the current. Good. So we can go back and say that initially we saw that this combination of the parallel was giving us a 1,982 ohms. We can just confirm that and see. If I get 2,975 multiplied by 5,95 divided by 2,975 times 5,95. Say plus. That gives me 1,982 roughly. Okay, so this entire thing is in series with this, which means that my effective resistance, okay, this is 8.5. Okay, I'll say 8.5. We said 1,982 plus what I just calculated, which is the 3,08, must give us 1,982 plus 3,08 gives us 5,062 ohms. This is the effective resistance. Then if I go back to the EMF, where I have I into R plus small r, we need the current, which will be EMF over R plus R. Substitute is 12 over, this is 5,062 plus the 0.2. Okay, punch this into the calculator. This is 12 over, you can say 5,262. 5,262, then that gives me 2,28 amps. Therefore, the new ammeter reading is going to be 2,28. Just round it off to 2,3. So that is what we end up with. That is what I end up with question number 8. Then question number 9. Question number 9. The simplified diagram below represents an AC generator with a coil that is rotating clockwise. Fixing wire to things the external circuit. Okay, so for as long as we're dealing with an AC generator, then we have to use the right hand rule. And the 9.1, what direction will the current flow? So using my right hand rule and then looking at the direction of the magnetic field, because now the direction is this. This is the B. And then it's turning clockwise. That's what they said. If I look at just this line alone, so which means the direction is up. Now that's just the up. Now they want the current. So the current must be moving from Y to X, which is that direction. So here I'm just gonna say Y to X. You don't need to explain, just use the right hand rule. Okay, so it's the right hand rule. That makes sense. Then 9.2 state the energy conversion that takes place within a generator. So we know that a generator is known for converting mechanical energy, okay, mechanical energy to electrical energy. Okay, mechanical to electrical. All right, then they're telling us that the maximum voltage, we can say Vmax, is 125V. Can we define what the root mean square voltage represents? So it's gonna say this is the AC voltage. Okay. Why am I saying voltage? Yeah, I can use voltage since we're talking about voltage. So it's the AC voltage, okay, which dissipates the same amount of energy. Okay, that is equivalent to a DC voltage. Okay. Then calculate the VRMS. So we know that from the formula page, VRMS will be Vmax divided by square root of 2. Just write that formula down, and then we do the substitution. So 125 divided by the square root of 2. 125 divided by square root of 2. 125. I'm getting 88.39. And then the total resistance is this, calculate the maximum current. So resistance has nothing like root mean square. There's nothing like maximum resistance or minimum, whatever. So what we can do, since they want the current, we can just use the V is equal to IR straight away. Okay, since they want the current, we know that current is going to be V over R. Now, since they want the maximum, I can just say Vmax divided by that. They give us the Vmax as 125. So 125 divided by 42.4. So V is equal to IR. And then do that. So if I say 125 divided by 42.4, that gives me 2.95 amps. Okay. Alternatively, since we got the VRMS, we can also do the substitution using this. And we have our 88.39 divided by 42.4. Okay, 88.39 divided by 42.4. That gives us 2.084. Then we just multiply this by the square root of 2, multiplied by the root of 2, and then you'll be able to get the same value so that you can change it to maths. Okay, then 9.6, the generator induced current at a frequency of 20 Hz. Coils that rotating from the initial position as shown in the diagram. Okay. So for as long as the coil is horizontal, this is when we experience the maximum EMF that will be produced. Okay. And then for as long as the coil is perpendicular, then we shall have less or minimum. So they want us to sketch the graph for two complete rotations. So what I'm going to do, I'll just say this is my frequency in Hertz. Okay, and then I'll have something like that. It is one complete rotation, and then I'll have the same thing repeat itself. So that is two complete rotations. So this is going to be 20, then down here I'll have a negative 20. This is time in seconds, because they said they want induced current. If I use the frequency, that is how it's going to be. So that is that. All right, then that is question number 9. Question number 10, the last question number 10. They want us to define photoelectric effect. So we're going to say this is a process, okay, whereby electrons are ejected. Electrons are ejected from a metal surface. Electrons are ejected from a metal surface. Okay. When light of suitable frequency, is incident or is shown on the surface. Okay. When we shine light of required frequency, then electrons will be emitted. So that scenario is what we call photoelectric effect. 10.1. So light of wavelength 4,7 times 10 to the negative 7. Let me jot it this side. Okay, 10,2 telling us it is 4,7 times 10 to the negative 7 meters. Okay, it's shown on the surface of this metal. If the threshold frequency is this much, so I'll say frequency naught is 4,37 times 10 to the 14 hertz. Okay, calculate the maximum speed of the electron ejected from the surface. And so we know that our maximum speed, you can look at the formula page and have E being equal to the work function plus the kinetic maximum or the EK max. So if I just try to use the formulas and do the substitution, we know that energy will be given as the constant, Planck's constant times the frequency, which is equal to the work function, which we don't know yet. So I can use Planck's constant and the threshold frequency plus a half mv squared. It's going to be max. Now we need the Vmax. Let's do the substitution. Do we have the frequency? No. They gave us just the wavelength. So this needs to change. C over wavelength is equal to HF naught plus a half mv squared max. Do the substitution, that's 6,63 times 10 to the negative 34. The speed of light is 3 times 10 to the 8. The wavelength they gave us is 4,7 times 10 to the negative 7. Let me subtract same time, because when I move this, it's going to be subtraction. So 6,63 times 10 to the negative 34 multiplied by the frequency threshold, which is 4,37 times 10 to the 40. This must give us a half multiplied by the mass. Now this mass is the electron mass, which is 9,11 times 10 to the negative 31 v squared max. Okay, so let's simplify the left hand side. So when I subtract this, I'm ending up with 13,347 times 10 to the negative 20 is equal to, when I simplify this, I'm having 45,55 times 10 to the negative 32 v squared. Just punch that in the calculator. Okay. Then I'm going to divide both sides and then put everything under square root. So 13,347 times 10 to the negative 20 over 45,55 comma 5, 5 times 10 to the negative 32 will give me my Vmax. So that is 5,41 times 10 to the 5. That is meters per second. All right, so that is 10.2. Then 10.3, we're being told that a simple electroscope consists of a metal stem and then a thin length of gold foil. When the electroscope is neutral, the foil just hangs back, as shown diagram. And then when the electroscope is negatively charged, the foil is repelled from the stem, as shown in the diagram. So we can see this, and see if it's negatively charged. Then when ultraviolet light is shown on the disk, it is negatively charged, the electroscope collapses. What this means that this light, after being shown, remember, this is negatively charged. So if the electrons are passed there and then we have negative and negative, that's why there is a repulsion. So what this simply means that ultraviolet takes away some electrons. Okay, and as long as electrons are removed, the stem will be more positive and it will cause some bit of attraction. So in other words, it neutralizes the entire system again. Then the question is, how does the frequency of ultraviolet compare to the threshold of zinc? Is it higher than, greater than, or lower than? Now, the fact that this light removes some electrons from this disk, okay, which means the frequency must be great because it surpasses the threshold. So we're going to say higher than. Okay, then we need to explain our answer. So one, we say that electrons will be emitted or will be removed from the disk. Now we can say electrons are removed from the stem via the disk. Same thing. Removed from the stem, via the disk. Okay. This makes the stain more positive or just neutral, which attracts, and the whole thing is back to zero. Then they're telling us that green light is now shown on another negatively charged electroscope. The foil does not collapse. What does this tell us? Will the foil collapse? The intensity of the green light is increased. Right? Yes or no? Give the reason for that. So the answer is a no. I mean, the fact that the green light has failed to make a collapse, which means the threshold has not been met. Okay. And then 2. Okay. So we can say that, 2. Remember, intensity has no interference with the frequency. So what matters is just the frequency, regardless of how much you bring about of the green light. For as long as the minimum frequency is not met, then it's not going to help. Okay, so the answer is a no. You can say that electrons are only emitted or are only ejected from a metal surface with a range of frequencies. Okay, and kinetic energy. So the number of electrons depends on whether the threshold was reached or not. Was reached Okay, so for as long as the radiation does not have the required energy and the threshold frequency, no electrons will be emitted. So guys, that is that. And then I just want to stop there and wish you guys all the best in paper 2. Remember, the disclaimer, this is just the proposed or suggested, it's not the actual memorandum, okay? So if there are any mistakes, if there are any errors, please, you're more than welcome to correct us through your comments and all of that. Thank you very much. And then I sign out.